Hello everyone, how's your day going? So, in today's lecture and in this series, I'll be explaining basic electronics. And in today's lectures, we'll particularly be focusing on PN junction diode and operation of them under different biasing conditions, their IV characteristics, their static resistance, and dynamic resistance. I'll try to explain everything as clearly as possible. And this is the first time I'm teaching, so yeah, there goes nothing. How are you all, by the way? Yeah, so I'll be explaining everything. We'll go into some concepts first. I'll be explaining some, like very low level concepts so everyone can hop on to this video. I know you're gonna watch this video at like 2x the speed, anyways. So I'll take it slow. I'll write everything out and yeah, let's have fun. So, basic electronics, right? So, first we'll talk about intrinsic semiconductors. Intrinsic semiconductors are nothing but pure semiconductors. What are semiconductors? Semiconductors are materials whose conductivity is between of metals, so conductors and insulators, right? So their conductivity is between of metals and insulators. So these are semiconductors. And we have two types of semiconductors, intrinsic semiconductors and then extrinsic semiconductors. Intrinsic semiconductors are pure materials which do not have any impurities introduced into them. So I've drawn the energy diagram of intrinsic semiconductors at absolute zero. So this chart is for absolute zero. Sorry. So this chart is for absolute zero Kelvin, absolute 0 degree Kelvin. So what are these, boxes I've drawn first of all? So this is our low energy band. So this is where so you do not need to write all of this because our syllabus is mostly numerical based. So we'll be dealing with them later on as well. But yeah, so this box is basically for the lower energy band where all the electrons except of the valence shell reside in. So the electrons in this band do not move into other bands. Other bands are just basically regions of energy, right? So let's take, for example, silicon. We have silicon here, our friend. Silicon has four electrons in its outermost shell, the valence shell, right? So let's suppose, like currently we're at 0 degree Kelvin. Now we raise the temperature a little, slow by slow, and the electrons, the little buggers inside the valence shell, will get excited and they'll move to our conduction band. This is conduction band, and this is the valence band where all the valence electrons reside in. So after they've moved to the conduction band, so we have some electrons in the conduction band, and by some I mean a lot, because even a little bit of silicon has like billions and billions of silicon atoms. So, and what happens when they leave the valence band? So in their place, they leave these little holes, right? Vacancies, we can say. So holes are just like imaginary particles, and you cannot even call them particles, to be honest. They're basically what we define, like we basically make our life easier with them in electronics, and like when we're studying electrical engineering or any such related field. So what happens is, so let's say we have an electron here in this position. Now it moves somewhere else. So let's say it's now here, right? What happens to it, this initial position? So we take it as a new particle, which we call a hole. Okay, so now this turns into a hole. So why is that significant? So let's say a lot of other electrons are around this hole, right? So a lot of other electrons are around this hole. what can happen is now these electrons can take the other electron's initial place because they're in the same valence band. Now, if they've taken its place, right, they leave a vacancy in their initial position. So we can say the hole has traveled from here to here. And then other electron can take that position. We can say the hole then has traveled from here. And that's the concept of holes and electrons. So some electrons go to the conduction band, some electrons most of the electrons are still in the valence band. But yeah, some holes are made in the valence band, some electrons are in the conduction band. So we have separation of charges, right? So in the conduction band, the electrons are free to move, and in the valence band, the holes are free to move. But on their own, they cannot really do anything because so that's the whole thing, right? But at least we have charges, like the charges are capable of moving around, and that's why they have this conductivity between of metals or conductors and insulators, because in insulators electrons cannot move like that, and in metals are basically atoms embedded into a sea of electrons. The electrons are free to move around. That's why the semiconductors conductivity or resistance is between of metals and insulators. So some examples are silicon and germanium, right? And another thing is like the temperature coefficient of resistivity, right? Alpha, if you remember from 12th class. So the alpha here for semiconductors, intrinsic semiconductors, is actually negative. So if you keep raising the temperature, more electrons will keep moving out of the valence band and going into a conduction band, and more electrons will, more holes will be made into the valence band. So this gives it more potential to conduct more electricity, right? So the temperature of coefficient is a negative. Increase in temperature leads to a decrease in resistivity in semiconductors. So now we moved on to extrinsic semiconductors. Extrinsic semiconductors are nothing but intrinsic semiconductors in which some impurity has been introduced. So intrinsic semiconductors on their own are not as much conductive as we want. So now we introduce some impurities into them. So what type of extrinsic semiconductors are there? We have two types of extrinsic semiconductors: N type and P type. So what are N type semiconductors? N type semiconductors are extrinsic semiconductors in which impurities with valency of 5 are introduced. So pentavalent impurities. Pentavalent impurities. So they have an excess of negative charge, excess of electrons these impurities have, right? Excess of electrons. In p-type semiconductors, we introduce impurities as opposed to n-type semiconductors. We dope them. So doping is the process of introducing impurities into semiconductors, right? We introduce trivalent impurities like helium and indium. Trivalent. They have they have 3 electrons in their valence shell. So here, N-type actually stands for negative material. Why? Because let's say we have some, silicon. Now that silicon has, I'm not doing a good job at making the diagram, sorry. So let's say we have a silicon atom. with 4 electrons. And then we have another silicon atom with 4 electrons. And then we have a pentavalent atom, right? With 5 electrons. And so on, right? So this, like, just imagine this like continuing on. So now we can see in this whole material, there will be an excess of electrons. Here's the extra 1 electron. So if you remember, if we go back to our, you know, energy band. So if there are excess of electrons, so that means more electrons will move into the free electron band, right? We have more electrons there. Why are there more electrons there? Because that extra electron moves into the conduction band, right? And the valence band still has like all the 4 electrons there. Like there are still holes, like because of the electrons that have moved to the conduction band, there are still holes, but electrons are the majority carriers. Majority carriers. So here the concept of majority and minority carriers comes into play. So in n-type electrons are negative. So n-type negative material, majority carriers are electrons, minority carriers are holes. In p-type, where there is a reduction in number of electrons, we have majority carriers are holes and minority carriers are electrons, right? Generally, in the like it's much easier for charges to move in the conduction band than in the valence band, right? So for that reason, n-type semiconductors are over 2 times as conductive as p-type semiconductors, right? So this is our whole concept of semiconductors: n-type semiconductors, p-type semiconductors, extrinsic semiconductors, intrinsic semiconductors. You don't need to know much more than that, actually. So yeah, now we'll move on to the concept of p-n junction. 2, 3. So in the previous topic, we discussed how we can get different extrinsic semiconductors by the process of doping. So this is all well and good, but these newly doped semiconductors do very little under their own because of their electrical neutrality. However, if we join them together, they behave in a very different way, merging together and producing what we know as a p-n junction. So as we know, p-type semiconductors have large amount of holes. Here, these purple dots or small lines. I'm very bad at drawing, so yeah, don't attack me on that. But yeah, so these purple dots are holes and the yellow ones are electrons. So as you can see in the p region, we have large amount of holes, very little amount of electrons. And in the n-type semiconductors, we have large amount of free electrons, but very little amount of holes. So when these two materials are joined together, we get a gradient of charge carrier densities at their meeting junction. So this is the meeting junction. And when we join them, so here, like in the n-type region, there's an excess of free electrons. P region, there's a deficiency in free electrons. So what happens is these electrons start crossing over and start going into the p-type region. And the holes in the p-type region start moving into the n-type region. So this process of charge movement of charge carriers from higher density regions to lower density regions is known as diffusion. Now, as these electrons from the n-type material leave towards the p-type holes, so right, they're going towards the p-type holes. They leave holes in their place, right? So we have like, so let's say the electrons that were here went there like into the p-type region. This is where the two materials meet, and the holes from there. Like now that they've moved here, like they leave holes in their places. So as a, like, we get negative ions in the p region, and then we get holes in the n region, right? So as a result, the charge density of the p-type semiconductor, right, of the p-type semiconductor along the junction, so this area along the junction is filled with negatively charged acceptor ions, Na, right, or acceptors. So we call them ions. And the charge density of the n-type along junction becomes positive because of the holes they left, holes in their place. So now this, like, now there's a gradient, right, a charge gradient between these two regions, right? So charges have moved, diffusion happened. This is also called as diffusion current. So diffusion happened, and this after a certain point reaches equilibrium, but we'll talk about that as well, right? So, and the width of these p and n layers, right? This layer and p layer and n layer depends on how heavily each side is stoped with acceptor density Na and donor density Nb, right? So as a result, the charge density of the p type, like, yeah, this process continues back and forth until the number of electrons which have crossed the junction have a large enough electrical charge to repel. So now, if lots of electrons have come here, right? Lots of electrons are now in this place. So let me clear it a bit. I hope you understood it. So now we have lots of electrons here. Now there is no, like, charge gradient, because these electrons, if they try to move over into the p-type region, these electrons will repel them, right? These will now repel these electrons. Hence, our gradient, or this movement of charges, will reach a sort of equilibrium, right? So this state of equilibrium will occur, producing a potential barrier zone, right? So this zone, this repulsion between electrons, will produce what is called a potential barrier zone around the area of the junction, as donor atom repels the holes, and the acceptor ions repel the electron, right? Now, since no charge carriers can rest in a position where there is a potential barrier, right? So we know that, like, if there is any potential barrier, no charge carrier will be able to sit in that region, right? So these electrons move out of this position to into the p-type region, and these whole move to the n-type region. And after some time, this whole part, right, this whole part now becomes completely depleted of any more free carriers in comparison to the N and P type materials further away from the junction. So this junction around the, like, this PN junction area, like this area around the PN junction, this is the PN junction where the P type and N type materials meet. So this area becomes depleted of all charge carriers. This area is called as the depletion layer, right? And this PN junction potential barrier that we talked about is, so this barrier is the amount potential that you have to apply using external sources, so like battery or anything else, so that these electrons can start moving again. So you'll come to understand about this later on when we talk about IV characteristics of a diode. But yeah, so so remember this: doped germanium has a potential barrier of 0.3 volts. We don't use germanium as in semiconductor industry anymore. Silicon is more preferred. And doped silicon has a potential barrier of around zero point 0.7 volts. Now we'll talk about PN junctions under bias. Let me clean this. I'll Okay. So now that I've cleaned it, and we'll move on towards PN junction under bias. So let's say if we were to make electrical connections at the ends of both our N type and P type materials and then connect them to a battery source. Now, an additional energy source now exists to overcome the potential barrier, as I talked about before. So, the effect of adding this additional energy source results in the free electrons being able to cross the depletion region from one side to the other. So, if I add a battery, additional energy source, and provide some potential across these regions, now these electrons can move from the N region to P region, right? So basically, the behavior of the PN junction with regards to the potential barriers width produces an asymmetrical conducting two terminal device. So this basically becomes a two terminal device, R diode, right? It has two terminals. This is also known as the PN junction diode, right? So this device, this PN junction material, like this mixed together when attached to an external battery source, is then known as a PN junction diode. So in circuit diagrams, so circuit symbol of a diode, first of all, let me draw that. The circuit symbol of a diode is like this. So this region is the P-type region, and this pointy region is the N-type region. So I've remembered it according to this. You can remember it according to whatever you want. Now there are three types of and the application of external voltage across the diode is then called biasing. So if we apply external voltage across the diodes, so this whole process is known as biasing. Now we'll talk about what kind of biasing there are. So there are three kinds of biasing conditions. So the first type is no bias or zero bias. So this is where we have not applied any sort of like additional energy or additional battery to the PN junction diode. Second is forward bias, and third is reverse bias. So let's talk about zero bias or no bias first. So this is the condition where there is no external voltage applied, and the movement of charge carriers across the diode. So let's say this junction, this deplete the movement of charge carriers across the whole diode is zero. Net flow is zero because we are not applying any external voltage between these diodes. So the electrons by themselves won't be able to cross this potential barrier that has been made, like they won't be able to cross this depletion region. Now, to do that, we need to move on towards forward bias. So, forward bias is when a diode is connected in a forward bias condition, a negative voltage is applied to the N type material and a positive voltage is applied to the P type material. So, forward is when N negative. So, negative is joined to negative. So, this is where it is in the forward bias condition. So, this is the negative N type region. We have applied we have connected it to the negative terminal, and positives we have connected it to the positive terminal. So we are applying this external voltage, right? Now, if this external voltage becomes greater than the value of the potential barrier, which is, again, I talked about it before, which is approximately 0.7 volts for silicon and 0.3 volts for germanium. The potential barriers opposition, right? These potential barrier opposition, these potential barrier oppositions that were being made will be overcome and current will start to flow. So this is because the negative voltage, right? So we can say, sorry, the negative voltage, wait, this is the P type region. That'll be reverse. Negative voltage, positive. So this is because the negative voltage pushes. So now there are like an axis of electrons in the battery, right? Excess of electrons. So this voltage will push these electrons to go towards the P region, right? And like they give, like it gives them the energy to cross over and combine with the holes being pushed in the opposite direction towards the junction. So like the positive terminal, negative positive terminal pushes the holes, negative terminal pushes the electrons, and these start combining together, right? They start crossing over the depletion region, and this results in a characteristics curve of zero current flowing up to this voltage point. So up until this voltage point 0.7 or 0.3 or any other voltage point is reached, till then like there will only be zero current. But after that, high current through the diode will start moving with little to no increase in external voltage, basically. So we'll draw this into a graph, and that'll be known as the IV characteristics of forward bias. PN junction under forward bias, we'll do the same thing, and that'll be known as the IV characteristics of PN junction under reverse bias, and both of them together will make the IV characteristics of a diode, right? So these terminals will start pushing them towards each other, and so this potential barrier, right, this voltage that these electrons need to overcome, and like the voltage we need to supply for the current to start to flow, this is called the knee voltage, right? This is also called the knee, and this I'll make the IV characteristics later on, but yeah. So this negative P junction is, this is negative, and region is connected to the negative terminal, positive, positive. They start pushing. So the negative terminal pushes electrons towards P region, positive terminal pushes holes to N region. And once they overcome the potential barriers, a high amount of current starts flowing through the diode with little increase in voltage. Now we'll talk about reverse bias. So you may have already guessed it. Reverse bias is when P type is connected to the negative terminal and N type is connected to the positive terminal. When a diode is connected in reverse bias condition, positive voltage is applied to the n-type material and a negative voltage is applied to the p-type material. So the positive voltage applied to the n-type material attracts electrons towards the positive electrode and away from the junction. So this positive voltage that we have applied, this will attract the electrons toward itself and away from this junction, away from this, away from this junction. And oppositely, like the holes will be attracted towards the negative terminal and away from the junction, right? And this will prevent current from flowing through the semiconductor material, right? However, the applied potential favors the movement of minority carriers across the junction. So here comes the concept about minority carriers, right? As we talked later, we talked before, n-type region carriers are holes. They are like very little amount. P-type electrons. So even though in reverse bias, these minority the majority carriers will be attracted to the terminal and this depletion layer will increase, right? This will start increasing. So if it's here right now, then it'll go here and here and here and here, and like the depletion layer will start increasing, and like current will be unable to flow. But these minority carriers, so the reverse bias is actually forward bias for the minority carriers, because we have holes in the end region, so they'll be able to move, like towards the negative terminal, and the electrons in the p region, the minority carriers will be able to combine with the holes from the end region. So this very, very small, like this current is in the amounts of nanoamperes. So this very small current is called reverse saturation current, and this reverse saturation current is represented by I naught or IS. IS. I didn't say that correctly. Don't go like, you know what? Any of you who watched this video, quote me on this one. Like, IS. Yes. Like, I'll at least know, like, if there's a comment with this in the comment section, I'll know, like, some of you at least watched the video, which is a very good thing. So, quote me on that. Comment it there. I'll reply to you. Let's go. So this is basically like check valve, a pipe under a check valve, right? So let's assume a pipe. Yeah. So we have a pipe here. And there's a check valve. Yeah. So now this check valve only allows the flow of water in one direction. Yeah. So water is blue. I hope it is. I cannot choose the blue color. Maybe I'm just colorblind. So if water is moving from left to right, right? Water is moving from left to right. This valve will open and this will allow the flow of water throughout the pipe, right? Now what happens in the opposite direction, right? So water will start moving from, like we have now the water has gone and our check valve is in like the initial position. Let me change the color. The check valve is in the initial position. Now what happens when water starts flowing in from the other direction? Nothing happens, because the check valve checks that the water only flows in a single direction. So now like this, the only thing water will do is like push the check valve more until like there are only two possibilities: water will stop or the check valve will break. In a like a similar analogy can be used later on when we talk about breakdown. But before that, we'll move on to some questions that you can like I'll ask you, and then like you can try answering them in your brain. So remember this water pipe thing, like is very good analogy for the PN junction diode under different biasing. So under forward biasing, it acts as like the water is flowing from left to right. So it allows the current, right? Under reverse bias, the PN junction diode stops the current, except the saturation current, which is like extremely minute, right? The first question is here. The arrow direction in the diode symbol indicates. Right? I already told you what is this part and what is this part. We already talked about it. The base is P type, and the end or the arrow is N type, right? Another question that could be asked, like when the diode is forward biased, is it equivalent to an on switch or an off switch, right? So diodes can be used as switches, if you didn't know. So is it an on switch or an off switch? Will it allow current? Is it allowing current in under forward bias, or is it stopping current? Well, we've talked about this as well. It is allowing current. So it is equivalent to an on switch. And yeah, that's it. Now we'll move to IV characteristics of diode. Right? So give me a minute or two to make the diagram. I'm gonna skip it anyway. But yeah, which color did I use? I've drawn this graph, right? So let's see what will happen when our diode. So this is the configuration of our diode. So positive, this is the P type P region connected to positive, N region connected to negative, right? When in forward bias, and in reverse forward bias, and in reverse bias, this negative turns into positive, and positive turns into negative. So NP, negative, positive. So that is forward. And when N is connected to the positive terminal and P is connected to the negative terminal, that is reverse bias. So under forward bias. So let's go at it, step by step. What happens? So first, current is at 0. Now, in real conditions, I talked about, until the knee voltage, like the current is at 0, but it's not really 0 because there is still some movement of charges, right? Still going on due to the minority carriers, right? So some very, very little movement. So we apply some voltage and it starts going up. And then we keep increasing the voltage, right? We keep increasing the voltage. And here we reach the knee of the diode. So we break its knees. So knee is, remember again, 0.3 volt for germanium, 0.7 volt for silicon. And as soon as we reach the knee, that was very bad, I'm sorry. Our current starts increasing rapidly with, very little increase in voltage. So after the knee, the current just starts like going up rapidly. Now, what happens under reverse bias? So there's always some small saturation current going on under reverse condition because of the minority charge carriers, right? This is also called the leakage current. It is less than 20 micro, right? Yeah, micro ampere for silicon and less than 50 microampere for germanium. So like there is like we keep increasing the reverse voltage, right? We're increasing it, increasing. Like what happens in real time when we have increased the reverse voltage so much? Like we've kept on increasing it. So after a certain point, it the whole diode breaks down. So how it breaks down, I'll talk about that later when we are discussing the reverse bias as well. And when it breaks down, it goes like this. Right, so this is also called the Zener breakdown or avalanche radiation. We'll talk about it, like we'll take an overview of why it happens today, and like in the next class, in the next video, I'll talk about like this in brief. So the voltage at which this have like Zener breakdown happens is called the reverse breakdown voltage. It's called the reverse breakdown voltage. So just a recap, when we apply forward voltage to the diode, the forward current is initially zero, then increases sharply after we have broken through the knee, right? After we have like our applied voltage has broken through the knee voltage. In this case, our diode acts like an open switch. It allows all the current through it. And in the reverse bias, the diode behaves like so. This behaves like an on switch and a closed switch. So remember that. I get confused with it all the time as well. On and closed. So closed is when our switch is in the closed position, and on, it's called on, and off or open is when our switch, there is some distance between like the two switch ends. So that's called the off or open position. So in the reverse diode, it acts like an open switch, right? But still, there is very little current passing through it due to the minority carriers. Again, this is also called the leakage current. Remember that. And after reaching a certain reverse biased voltage, there is a certain surge of current due to breakdown phenomena, and the voltage is known as the reverse breakdown voltage. So now we look at them one by one, right? So the application of a forward biasing voltage on the junction diode, this results in the depletion layer. So remember the depletion layer that we talked about? This. So under the application of forward bias, this depletion layer keeps on decreasing and decreasing until we reach the knee voltage, and then it disappears, and the electrons and holes, start merging, like start exchanging, and we have current going through the diode, right? Become like very thin and narrow, which represents a low impedance part. So like this, like there is still some depletion layer, but it's like very, very, very narrow, right? So this allows the flow of current, and yeah, and after the knee, the forward current just like shoots up, right? It allows unlimited amount of current, and not unlimited because there is always some dissipation of energy because of the minority carrier. So like it cannot go unlimited. It'll break down. Same way, reverse breakdown. In the reverse breakdown here, the diode will be destroyed. So now we'll talk about the reverse biased characteristics, right? So like the graph is also shown as this. So like there's this box, very bad box I have made there. And it goes like here, and we have the breakdown voltage, and it starts going like down rapidly. That's also called the avalanche reverse breakdown phenomena, avalanche phenomena. Yeah, and so that we know there is a small amount of current flowing through it called the leakage current. And if the reverse bias voltage applied to the diode is increased beyond certain limits, there will be a large current due to the avalanche effect and cause breakdown. So this avalanche effect is where like the electrons, we remember our p-n junction depletion layer increasing a lot, right? We remember that like the p-n junction layer increased like a lot, like it becomes very big. So like there's still some electrons here, right? Lots of them. So if the energy is enough to kick electrons out of the valence band or even the lower energy band, so if they're kicked out, they might have enough speed because of the reverse voltage that they'll kick out other electrons as well, and then they'll kick out other electrons, and there will be a chain reaction, and all of those electrons, like billions and billions of electrons, will go towards the end region at the same moment. This will lead to a break. Like this is what's essentially an avalanche, right? Like a single pane of snowflake. So a single snowflake, not a single, like it's like avalanche happens when like bigger things than snowflakes get detached. But yeah, we can say like a single snowflake causes a whole avalanche to happen, right? So now we'll move on to the diode current. Very important part, right? The diode. So this current flowing through the diode, like it's not a straight line, right? This is not like this our device is not following Ohm's law. So we have an equation of it given by Shockley. It's also called the Shockley equation. Shockley was from Bell Labs, and we have a lot of things coming out of Bell Labs. Our programming language C also came out of Bell Labs. And yeah, so this equation is nothing but ID equal to I naught multiplied by exponential VD over eta VT minus 1. So here ID is the diode current. I naught is the reverse saturation current. Diode current is like the current flowing through the diode. I naught is the reverse saturation current. VD is applied bias voltage. So VD is positive for forward bias, right? VD, so this is the voltage that we apply. VD is positive for forward bias and negative for reverse bias. So the derivation of this equation is like extreme. Like this is that is out of our scope. Like if you want to learn that, go to electrical engineering, which I'm sure not many are doing. But yeah, so VD is applied bias voltage. VT is our voltage due to the temperature. Yeah. So you remember when we talked about like electrons getting kicked out, and because of that, like between the two minor like between minor charge carriers, like there comes a voltage which is given by Vt equal to T over 11,600 volt, right? T is in Kelvin. T is in Kelvin. Eta is a constant which is 1 for germanium and 2 for silicon, right? So for large forward bias, this equation, or Shockley equation for large forward bias, for large forward, so any bias or any voltage that we see in our daily life is basically a large forward bias or large reverse bias. So the large forward bias, this equation, this Shockley equation, approximates to ID equal to I naught exponent of Vd over eta Vt. And for large reverse bias, ID is equal to the negative of the saturation current. So you have to remember these. You have to remember the Shockley equation, very important equation, very, very, very important uh, equation, right? For large forward bias, ID is equal to I naught exponent to Vd over eta Vt, and ID equal to negative I naught. Let's make it, instead of I naught, let's say Is, or saturation current, negative of the saturation current. That is, like for large reverse bias, that is the, like all the current that flows through the diode. We can see that here. That is like this Is is all the current that flows for large, voltages before the breakdown voltage occurs. So the reverse saturation current is a temperature dependent parameter, by the way. So it doubles every 10 degrees Celsius rise in temperature. Okay. So this reverse current, like, which is due to the minority charge carriers. So the minority charge carriers in N-type material is holes, and P-type material is electrons. So more temperature means more holes and electrons getting out of their, valence band and going into conduction band, and more holes being made into the valence band. So these move, and so more temperature, more current. What's the relation between them? So for a journal, remember this technique, just remember 10 degrees Celsius, not even Celsius, just take it as Kelvin. It doesn't matter. For every 10-degree Kelvin increase, it doubles, right? For every 10 degrees, it doubles. The formula would be I not 2, so final, or let's say I saturation final, ISF, saturation final, is equal to I saturation initial current multiplied by 2 times 2, and then to the exponent. In the exponent, we have T2 minus T1, where 2 is our final current, final temperature, and 1 is our initial temperature over 10. So let's say temperature is increased by 10. What happens? ISF equal to ISI dot 2 10 over 10, which becomes ISI multiplied by 2, which is 2 ISI. Right? So it doubles. Every 10 degrees, it will double. And if you have any two, so if 20 degrees, then it 4 times, 30 degrees, 8 times, 40 degrees, it goes into the power of 2, right? Now that this is over, we'll talk about diode resistance. So diodes also have, resistance. There are mainly two types of diode resistance, DC and AC resistance. So let me draw the graph. So we have the graph or IV graph of forward bias. So in forward biasing conditions, static resistance. So diodes under DC voltage have an operating point where like where they like to operate, and it stays constant throughout their operation, right? So this operating point is found, like it's being found out by making the load line, which might come later. I don't know, I haven't read the syllabus like that far away, but basically the resistance, like under DC conditions, it follows Ohm's law, ohmic law. It can be written as RD equal to VD over ID, right? The DC or static resistance of a diode does not depend on like the curve of the shape of the curve. It depends only on the operating point, or the values of diode voltage and current. It has nothing to do, like under DC voltage, it has nothing to do with the curve, the resistance, static resistance. Now if we talk about dynamic resistance, let me clear it out a bit. So there are two ways to find out the dynamic resistance under forward biasing conditions, right? So first is to simply get the slope, right? First is to simply get the reverse of the slope. So 1 by slope. How will you find the slope? Well, it'll be given in the graph. That's a very bad line, but I mean, what you gonna do? Del V D and boom, del I D, and dynamic resistance RD would be 1 over slope, or equal to del VD over del AD. This is the dynamic resistance of a diode under forward bias, right? Another way we can find this is through the Shockley equation. There is a derivation of it, but even in that derivation, there are a lot of approximations. So I wouldn't like a lot pages worth of approximations. So, but still, if you want to know, we know the Shockley equation is ID equal to I naught e to the power Vd over eta Vt minus 1. Under large forward bias, it becomes ID equal to I naught dot E Vd by eta Vt ID, and now you take the derivative of it, differentiate it with respect to Vd, our bias voltage. So dId by dVd equal to d by dVd multiplied by is e Vd over eta Vd minus 1, which becomes is over eta Vt e to the power Vd over eta Vt, right? And through various approximations, this certain equation, and when we reverse this expression, it becomes dVd by dId equal to eta Vt over Id plus Is. Now, we know, like in certain conditions, Id is extremely larger than Is, right? So this equation basically translates to dVd. I wouldn't do that. So RD, dynamic resistance, equal to dVd over dId equal to eta Vt over It. And for, let's say, for germanium, right? For germanium only, eta is equal to 1 and Vt is approximately equal to T over 11600. So at room temperature, at room temperature T equal to 300 Kelvin, RD becomes dVd by dit 300 over 11600 dot it. This you basically have to remember. I tried finding the derivation out on Google in approximations, and they have to approximate a lot of stuff, which is, yeah, I don't even know if they'll teach us that in BTech, engine electronic BTech. Yeah, make sure to remember Shockley equation. Shockley equation under large forward bias and reverse bias, and this this is also equal to RT, right? Make sure to remember that. All right. Everything else you can derive on your own. So make sure to remember Shockley equation, dynamic resistance. So these are the only two things that you have to remember. And of course, the eta value for germanium and silicon. But I don't even think that you have to remember this because they'll give us formula books and like these formulas should be in those books. But still, if you want to remember them, you can remember them. But yeah, now there are two types we'll talk about, like just to end this lecture, we'll talk about ideal diodes and practical diodes. Ideal diodes are nothing but switches. Ideal diodes, just pure switches. Like the IV graph of ideal diodes basically goes like it goes to a knee voltage, and then the current just goes infinitely high, right? IT. And at like in the reverse bias, like in an ideal diode, like there is infinite resistance, so there won't be any flow of saturation current or anything like that at all. For practical diode, we have been studying practical diode till now. Here's the IV characteristics for the practical diode. So in practical diode, so an ideal diode can conduct an infinite amount of current and it can block an infinite amount of current. But in a practical diode, you have certain values that you cannot go above even in forward biasing, or the whole diode will break down, and you have certain voltages that will break down the whole diode due to the breakdown phenomena, right? So we have done ideal diodes, practical diodes. We've talked about diode resistance. We've talked about IV characteristics of diodes. We've talked about PN junction under bias, concept of PN junction. Yeah, and let's go to some problems now. Yeah, this will be the last thing that we'll do today. Some problems. So first, so we have a silicon diode which has a saturation current of 1 picoampere. Wait, or I'll do the problems in the next video. Yeah, that would be much better to do the problems in the next video. Won't you say? So like we can just refresh your memory, but you can also find out some problems on this and you can do those problems